machine learning and AI for the past 10 years. So initially started with in academia at UCL, and then moving into consulting, mainly working with consumer goods and retail and market research. And my focus is really around like the application of large language models in consumer facing industries. So whether that's market research or retail or consumer goods. So today I'm going to be talking a bit about large language models in production, helping people understand different use cases, the process of to follow while building large language model based applications, and some of the challenges. And then we'll be talking about some specific industry use cases as well. So without further ado, I'll share my screen. And if you have questions throughout the presentation, please do just drop them in the chat and I'll get to them in the end. I'm keen to hear everyone's ideas, thoughts, and questions. So please feel free to ask while I'm presenting. Excellent. So I'm assuming everyone can see my screen. Let's move this over here.
Yeah,
excellent. So today we'll be discussing a number of things related to large language models. I don't know, there's a lot of people attending, so there may be some of this may be new to some people, and some of this may be ground you already cover and know quite well. So, if it's new, that's great. If it's something you already know, just be patient. We might get to new information, or it might help reinforce knowledge you already know. And we'll be covering a number of things. So firstly, we'll be talking about the fundamentals of large language models, helping understand some of just the core concepts. We won't be getting into the mathematical detail and the architecture of transformer-based models due to time, but we'll be talking at this at a high level. We'll be then talking about building large language applications. So this understanding the step-by-step process around selecting models and prompt engineering, fine-tuning, and integration into ultimately a successful application. We'll be talking about the concept of retrieval augmented generation, which is a common approach to incorporating domain knowledge outside of the large language model itself. And then we'll be talking about actually deploying large language models in production, some of the challenges, the limitations, but also some of the best practices and ways of mitigating those challenges. And then finally, we'll be talking about some real world use cases. And at this point, I also encourage you to think about within your own industry or areas that you're familiar with or passionate about, to think about use cases. And I think it'd be great to discuss that at the end, because I think there's a lot of hype and promise with large language models, and a lot of investment on the within companies like NVIDIA and GPU, in terms of GPUs, and then with some of the foundation model companies like OpenAI, Anthropic. But I think where there's currently the gap is actually finding the value within different sectors. So that's where I think practitioners come in, and that's I think what the gap that needs to be bridged to make sure that the application matches the hype over time. So the motivation, I think, so why are we talking about large language models? So I've been working in natural language processing for the past 10 years, and it's come a long way since then, and even before then. The idea of using computers for translation goes all the way back to the 1940s, would you believe it? So it's not like this has come out of nowhere. There's been a long process of the concept of neural networks, concept of natural language processing. But originally, a lot of that was done with symbolic models, which are kind of hard-coded rules to understand language. And then in the 90s, more like statistical rules. And then within the 2000s and 2010s, starting to use neural networks, and the result of Moore's law and the abundance of data and computation we now have available has really allowed this proliferation of large language models. So the application really is standing on the shoulders of giants in terms of the data available, the compute available, the energy available, and all the research over the past decades to get to this point. And with the emergence of the transformer-based architecture, which underpins most large language models, and the abundance of data and training time and compute cost has enabled large language models to really show a fundamental shift above traditional natural language processing and outperform them massively on a lot of the NLP benchmarks. But alongside that, have emergent capabilities for things that people didn't even expect and enable new use cases, new domains in the realm of natural language that were previously unavailable. And just to give a couple of examples in the real world where this is being used. So one company called Harvey are using OpenAI's large language model for trained on case law. So this can help people with things like drafting legal documents, answering questions about complex litigation scenarios, and finding discrepancies between hundreds of contracts, which would take a long time for paralegals or lawyers to do. Another example is Klarna, a payment application, and this is being used to automate a lot of Klarna's customer service. They claim it's doing the work of 700 full-time agents, and estimated to drive a lot of value there. So I think we're starting to see large language models in the wild and actually having tangible value, and I think that should really be the aim. So some of the fundamentals of large language models, just a quick definition. Essentially, they're a category of foundation models trained on huge amounts of data, and they make generating natural language available on a large range of tasks, which we'll talk about later. And some of the more well-known ones and the state-of-the-art models include GPT-4 and more recently GPT-4o from OpenAI, Google's Gemini, Anthropic's Claude 3. And Meta's Llama. So there's already a range of providers all competing to produce the most capable large language model. And I think actually because of that competition, it's becoming somewhat commoditized, which I'll touch upon later. But it's good to have this choice. So as a practitioner, having the ability to choose between different models and also that competition driving down cost is a good position to be in, and I can imagine that we'll see these models continue to improve and compete with one another. So what do we mean by large language models and foundation models? So large language models is generally these models are based on deep learning neural networks trained on massive data sets to answer natural language questions. Within those, there's a category of what we call foundation models, and these are more like general models that can be fine-tuned or used for different things. So things like GPT-4 or Gemini or more in the past, things like BERT and BART are generalized models to solve a range of tasks. So that's what we mean by foundation model. And how are large language models trained? How do we actually get to this point? I'm not that this is a very much a simplification, but should give a good understanding of the process towards training large language models. So the starting point is collecting all the relevant data, whether that's from large data sets like Common Crawl, which is scraped off the internet, or through textbooks, Wikipedia. Recently, OpenAI partnered with Reddit to be able to train on their data. So it's a huge, vast amounts of data in the trillions of tokens. The next step after collecting that data is tokenization. So this is basically splitting text into its relevant components. So a token might be similar to a word, but there's different types of tokenizers, which may not exactly be a word. It may be like a stem of a word. But this basically allows the encoding of text into a numerical representation. And then the step after that is what's called calculating embeddings. So embeddings is essentially taking tokens, which are the representations of the words themselves, and then understanding where they fit in what's called an embedding space. So this is like a multi-dimensional space of vectors, which show the relationships that words have between one another. So for example, you can see in this representation, this is just these embeddings projected onto 2 dimensions, that dog is close to puppy and van is close to car. So you'll have these token embeddings. You might also have positional embeddings to show where a word is within a sentence. But this embedding process provides greater meaning than the words themselves. So the model is able to then understand the relationship between different words, and that one word may be a good synonym for another, for example. And then the next point is around the pre-training of the transformer model. This is how traditional transformer models were trained, using backpropagation in this training process. But one reason models such as GPT 3.5, which was when that came out, that was presented as ChatGPT. It was the first time it became more in the hands of people, but had already been, worked on with researchers. One way that the large language models managed to improve upon previous models that had this pre-training process was to also incorporate an additional process called reinforcement learning from human feedback. So this is like essentially an additional training step which takes human feedback, which labeling outputs between different potential candidate models as better or worse, and then using a reward model to score those, and then basically train the model further to give more ideal outputs that a human might prefer. And beyond that as well, now modern large language models also have a mixture of experts architecture. So it's not just one large language model. Behind the scenes, when you use something like GPT-4, I believe for GPT-4, there's 16 different a mixture of expert models, which all contribute to the output that you finally see. So there's a lot of engineering research that goes into the training and fine-tuning of these large language models. But the final output text behind the scenes would be a representation of a vector, and each word would have a probability. So essentially, when you're seeing the output stream to your screen, when you're using something like ChatGPT, it is generating token by token, and the most probable token is predicted. And there are ways you can choose the different settings in terms of how likely each token is going to be. Like how the model will select different probable tokens, which we can talk a bit about later. But I think it's worth understanding that this is you are literally seeing like a token by token generation. So certain tasks which involve recursive thinking or large language models sometimes struggle with, which might be easy for humans, because it's even today large language models still are generated basically generated each token by token, depending on which is the most probable. Okay, so how can large language models be used? They can solve a wide range of NLP tasks. So beyond in the past, natural language processing, you would have a separate model for summarization, or a separate model for translation or content generation. With these more general models, they can solve many of these tasks. So you can ask a GPT-4, for example, to translate between 2 languages, and also classify a text, say classify a news article as being a sports article or what have you, or work within chatbots. So they are a lot more generalized. And these are some of the tasks that large language models can solve, amongst others, which we'll just touch upon. And I'll share these slides if you want to look in more detail. So one is around content generation. A lot of companies are starting to use large language models to generate like job descriptions. They might be generating marketing content, blogs. They might be using it for question answering. If you're going to a website and you want to ask a question about the FAQs, it can quickly give you an answer. I'm sure many people have used ChatGPT to ask different questions. Another thing might be data to text generation. So let's say you had structured data within a company, but you want to present it in a way that's in a report or in a text output, easier for people to read. That is one way large language models are used. Another thing is named entity recognition. So this is useful amongst a range of industries, but basically pulling out different entities within text. So you might want to, for example, find all the brands mentioned in a social media post, or you might want to find all the people mentioned within an article. So entities can represent a range of things, but some common ones might be a person, an organization, a location, etc. Code generation. I think the emergent properties of large language models mean that it's very helpful for code assistance, and GitHub have an AI-based code assistant, GitHub Copilot. And I'm sure anyone who's working on this call who works with code has used large language models to either review or test or generate code. And I believe that Meta are also using it for generating unit tests. So saving a lot of time for in development. Text summarization. So when you have large volumes of text, let's say, for example, a lawyer is reading through a huge case file, being able to summarize that quickly can save a lot of time. And I think that's one way I use it quite often is if I'm signing a contract or reading through an article, I might just throw it into Claude or GPT and get a quick summary. Text categorization. So this is basically classifying text into different categories. This might be, for example, a very obvious example is spam filtering. So when you're getting an email, there's probably an NLP model behind the scenes flagging what might be spam. Translation, I think, that's Google Translate's been around for a long time, and more recently with OpenAI's voice-to-voice native model, the ability to just translate it immediately between one language and another with incredible accuracy is really going to make the world a smaller place and easier for people to communicate. And also adjusting the tone or level of some text. So you may have written something, but you say, oh, I want this more formal, I want this more professional, I want this more casual. Or you might want to say, okay, I'm reading this paper, but I'm not at this level to understand all of the details. Could you rewrite it at a level of my ability? Or you're teaching a child or a relative or student, and you might say, oh, I want to explain this like I'm 5 or 10. So it's really useful for that use case. And there are many other use cases alongside these and emerging use cases all the time as large language models become more capable. Okay, so what are the large language models available and how do they compare? I mean, this is always changing. I mean, this is from today, but within a few months' time, this may look completely different, and there are many different benchmarks and leaderboards. This is one that I used from a company called Vellum, and this is showing some of the most common large language model benchmarks. So MMLU is one of the more common ones, which has a range of language tasks. Also, there's a math benchmark and one for coding called Human Eval. You can see across these GPT-4o, which is OpenAI's most recent model, is ahead, but there's not a lot between them on things like MMLU. And I do take these benchmarks, and I think you should take these benchmarks with a grain of salt, because there is always the chance of I wouldn't say cheating, but basically training on the test data, and the test data for these is often leaked. So if that test data is available to the large language model during training, it may show it being more performant than it would be otherwise. So I find that leaderboards which humans can compare the outputs are better, and also generally having I've seen it referred to as vibes, but some people suggest that actually getting a feel yourself of the language model output, maybe having your own set of tests. I think vibes is probably too casual and too not rigorous enough. But if you're using large language models, like actually testing it, even though one might be the have the highest on the benchmarks, actually testing it yourself is always important. And if you look at a model comparison as well from the same source, you can see that actually Claude 3 Opus is ahead across many of these. I really enjoy using Claude 3. Gemini 1.5 is also becoming available, has a huge context length. There's also open source models. Meta have done a great work in terms of training the Llama 3 model. And Mixtral from a French company called Mistral is another great open source model. So it's great to have these open source models available where you have more control. You can fine tune them further. They'll probably bring the cost down. So I'm really hoping that open source catches up with these premium commercial models. And there's also other things to consider alongside performance. You need to think about the cost, the latency, maybe there's rate limits. So all things to consider. But I just wanted to just give a quick overview of kind of the state of the field as it is at the moment with large language models when you're thinking of which ones to try out and use within any application. Okay, so now we'll get more into the heart of building large language model applications. This is an emerging field. I think the best practices are always changing, and I think you can only gain from experience. And beyond this presentation, I also recommend that you look at what information is out there. There's some great guides from some of the companies themselves, like OpenAI, but also guides that the community has put together on building production large language model applications. But I think going with the intent to build something reliable and robust and useful is important. I've worked in machine learning, data science for the last 10 years, and there's a lot of hype around things, but there's also a lot of bad practices and a lot of over promising and under delivering because just of the nature of the field and the lack of time often that's available or skills or knowledge. But I think we really need to have a similar approach to what has evolved within software engineering and DevOps, where we're using some of the best practices to develop things that are robust, reliable, not as prone to hallucination. Because I think the last thing we want is with all this hype that, I'm sure you've seen in the news, like different Google having issues with some of the answers it's giving with their Google summaries. I'm not saying it's easy, but I think if finding use cases where you're sure that you can have consistent output and using some of the approaches we'll talk about will add credibility to yourself as a practitioner, and also add trust with the work that you do, and also trust in the industry as a whole. So I really like to emphasize that. Okay, so what are some of the stages within building a large language application? So the first stage of any project, but I think an important stage that's often overlooked, is identifying the right use case. So there are many situations where companies may want to do AI. And you'll hear companies saying, we're setting up a data science team or an AI team and we want to do AI, and whatever that means. But they don't know how they want to use large language models or traditional machine learning. And there may be some use cases which have a lot of time and investment put into them. But even if they are successful, even if they do what is intended, they might not be applications which have some underlying value and tangible bottom line value for the business or organization. So really thinking hard about, in different scenarios, what will the value be in terms of, will it help the company generate more revenue? Will it reduce risk? Will it help cut costs and improve like operational efficiency? I think going back to these examples I showed earlier, there's some clear outcomes here in terms of it's saving time from agents. Here it's saving time from lawyers. That's clear operational efficiencies that you can put a number to. So I think like spending the right time to long list all the applications that you may have of a large language model within your team or organization, and then evaluating each on their potential benefits as well as the challenges. Do you have the right data available? Is it something that large language models are currently capable of doing? Certain things, for example, even simple arithmetic and mathematics, the frontier large language models do struggle. I often, when I see one of these LLMs released, just ask it to take an average of a set of numbers, and it gets it completely wrong. So understanding like where the limitations are, what it can't do well is also important, and what it can do well. And I think going back to actually some of the more traditional NLP tasks that we touched upon here are good places for large language models. So thinking in that respect, and also understanding your business, asking questions of interviewing business facing people as to what would be helpful, and then thinking about actually the financial impact. Or it might not be financial. It might be if you're working in the public sector or the charity sector. That actually what's the human benefit and the social benefit that it has. So once having done that and really identifying the right use case, starting with the most promising one, then the next step is around choosing the right foundation model. So you might want to evaluate different proprietary or open source large language models, and you may have different requirements in terms of capability. Cost might not be as much of an issue, so you can just choose whatever performs the best on your initial data. Latency, how fast the model can output tokens if you need a very quick responses. That might be a big factor. The rate limits, you may be estimating how often the large language model is going to be used, and if you're hitting rate limits, that may cause issue for the user. And of course, cost. If you're expecting to be processing, millions and millions of tokens, and you have a limited budget, then taking that into account, and maybe choosing a less capable model that is cheaper, or use self-hosting an open source model could be a good decision in that scenario. So once you've chosen the optimal foundation model, then there are various ways you can customize the output, which we'll talk about in a lot more detail later, through prompt engineering. There are many good prompt engineering guides and techniques to get ideal output. You may want to inject relevant context from internal data or user data via retrieval augmented generation, which we'll talk about later. And then also fine tuning. So we'll talk about fine tuning, where it can be used, where it's less useful actually, and the process of doing that. So I think once you've then customized a large language model to give the ideal outputs, this is really the probably the most complicated step, I think, for most people who are from a data science or ML background, who may not have worked as much in like software engineering. They may be lucky enough to be working in a team where there are people with more solution architecture and software engineering skills, but actually designing the correct appropriate solution architecture to deploy the model and integrate into another system, maybe via an API, or integrate with the user interface. Again, that could be via an API or within another communication mechanism. And finally, testing, deployment, and maintaining. In machine learning, evaluation is always incredibly important. So spending time to conduct thorough offline evaluations on test data. There are evaluation frameworks out there. There's one I can talk about those a bit later, but actually none of them are perfect, and using human annotation and human evaluation is still, I think, an important step. And then also online evaluations, before doing a full deployment, you can have a test deployment, what's often called like a blue-green deployment, where you have a large language model or any ML system operating like online responses before it's to either like a private internal group or a alpha testing group, beta testing group before then going into full production. And then finally, monitoring and maintaining the solution. Have you got a way to capture the text inputs and the generated outputs? Are there ways that users can vote up or vote down your responses so you can see what's actually working well and what's not, and maintaining the solution over time? With any software product, and the life cycle doesn't end at deployment. It's not like you deploy it and you walk away. It has to be maintained over its full lifetime. Okay, so we'll talk a bit about retrieval augmented generation in more detail, which is around this part around customizing the large language model. And this is a common approach to incorporating internal knowledge. And for many use cases, for many industries, retrieval augmented generation is a way of doing that, and is a way of building applications that are not just a GPT wrapper, but they're actually incorporating domain specific or company specific or user specific information. So the standard way we interact with large language models is you have a user prompt, and I'm sure everyone on this call has done this. It goes into some black box of which we call the large language model itself, and then a result is generated and streamed out to your screen. The problem with this is it has only the data available in the prompt and what is the large language model has been trained on. So if you have a use case, let's say, for example, that legal summarization use case where a law company has millions and millions of documents, or you're working within financial services and there are many, many financial reports and documents that you're trying to analyze, or within, let's say, healthcare, there's many patient notes, obviously that would have to be incredibly secure, but you wouldn't be able to get that just by asking ChatGPT, tell me about this patient, or tell me about this legal document. So this is where the approach of retrieval augmented generation comes in. And the standard approach nowadays is to take that internal data. So you'll have an internal corpus of documents that could be internal PDFs. It may be call center replies. It may be FAQs scraped from a company website, your own internal company website. It may be just internal corporate documents. It could be a whole range of things. One particular example I worked on recently was we were working on video surveys, so long form qualitative video surveys, as opposed to kind of the multiple choice surveys that most people do for market research. So users would answer a video on their phone talking about a brand, let's say Netflix, that we then transcribe that using Whisper, which is a speech to text model. And then that would form the documents that would be in our corpus of documents. Corpus just means like a large document data set. Then you would chunk the text into the appropriate chunks. This really depends on the domain itself. So the chunk often is best if it relates to the data and the domain. So let's say, for example, you're chunking PowerPoint outputs. One chunk might be one slide, or if you're chunking patient notes, one chunk might be one entry in the form. So it really depends on the domain itself of the choice of chunking method. Then once you've chunked that text, you'll then calculate the embeddings on that text. So this is basically taking those chunks of text and then with the embeddings that we mentioned earlier, representing those in what's called an embedding space, so that then it has more contextual meaning of how that document relates to other documents and other words. And then you'd store those embeddings in a vector database. So there are many vector databases available. such as Pinecone, Weaviate, Milvus that have come out recently. There's also, I think, something within, if any of you work with Postgres, which is like a more common SQL database called PG Vector. So you don't always need a specific vector database if you want to do retrieval augmented generation. So that's another approach. So once you have that data stored in a vector database, then when a prompt comes in, let's say it's a question asking about, let's say you have an application that is answering questions about the availability of products within, your local Argos store, like, and the user comes in and wants to ask, is this watch available in any stores near me, let's say. So the prompt may come in and ask about this, mention the particular watch, and that would then be the embedding calculated on that prompt, and then either through what's called semantic search, looking at the most similar embedding in the stored data via something called cosine similarity, or using keyword search, which is often as effective, or a hybrid of the two, hybrid search, so using both keywords and using the embeddings. So based on that input, finding the relevant response. And you may find in the database that, oh, okay, in the data that we have an entry that says this Casio watch, let's say, is available in, let's say it's available in Stratford, Argos, and this many are available. It could then answer that question, match the relevant text, and then put that relevant text into a prompt. And then you'd have a prompt that say, based on this entry that's come back, or set of entries, you may have like a range of things that matched, generate a large language model output, and then the large language model will come back and say, here are the details about this watch. If someone's asking, let's say they're not asking about availability, they're asking about different information about the watch's materials, etc. But then it could generate that result. So this is a really effective solution to incorporating internal data. It also gets around one of the issues with context length, because of the scaling laws associated with large language models and the attention mechanism, which transformers and large language models use. There is a limitation on the context length, and even with some of the larger context length models, they often decline in terms of accuracy at those larger context lengths. So keeping a tighter grip of the context length and using retrieval augmented generation is currently an approach, a common approach to doing that. It may be the case that in the future, retrieval augmented generation, actually becomes less prevalent because future large language models and architectures are able to handle huge amounts of text without the need for this approach. And there may be certain situations where actually you're building an application where you just need the prompt and some prompt engineering and the user's input to get you the result, or you already know from where the user is on an application or some filtering that's already been applied, what data needs to be included in that prompt. So you don't always have to do retrieval augmented generation, but there are many use cases when it is a good approach at the moment, and that may evolve over time. So with that in mind, what are some of the approaches around and things to watch out for when deploying large language models in production? So there are a few challenges around productionizing large language models in an application. The first of which is hallucination. So large language models are probabilistic in nature, and there is a chance, and I'm sure you may have seen this if you've interacted with them long enough, that a large language model may output text that is factually incorrect or not what it was intended by the user, with a lot of confidence. And this can cause a lot of issues. Imagine, for example, in a medical situation that you have a large language model that's providing medical suggestions or advice, and it hallucinates something that is completely factually incorrect and may harm the patient, that's something that could be disastrous. And to give more of a real example, the way Google with their summaries were using large language models on, I'm assuming, search data, it was hallucinating crazy suggestions of what people should do based on on the questions they'd entered into Google, and I think they quickly either took it down or changed that. So this is something that even the bigger, the top companies like Alphabet and others struggle with. So that is one issue. Another is obviously cost. Another might be the rate limits and can you serve all the customers that you need to if you're using an API. And the latency as well. Like, are the responses coming back fast enough? And the context length as well. Are you able to fit the text into the prompt that you need to? Yeah, those are some of the issues. I think there's others such as like bias and fairness, but we'll just touch upon those. So what are some of the ways to address those issues, such as hallucination, and others? So there's a really good guide that OpenAI put together on a general approach, and I think it's a good way of thinking about things in terms of optimizing solutions, and thinking about the different techniques you can use and in what order to use them. So there's a general flow of what you should do first to get from basically, your base model, base output to your ideal output. The first of which is prompt engineering. So a lot can be done just improving the way you've written your prompt, making sure it's very clear and explicit. Often it's just about rewriting something there's no ambiguity there. It's a very clear set of instructions that the large language model has to follow. And often the best approaches you'd use when giving instructions to a person also apply to giving instructions to large language models. And there's all the different prompt engineering techniques, certain keywords that people have found. You may have seen this, take a deep breath and think through step by step and things like that may squeeze extra performance out of a prompt. But this is a good step to start with prompt engineering and see how far that can get you. Then beyond that, there are two kind of dimensions to think about. One is what the model needs to know. So if you want to include relevant information outside of what the large language model has been trained on, it might be about your company, it might be about what's on the internet, what's been you've pulled from third-party sources. It could be a range of things. To include that context and what the model needs to know, like incorporating knowledge. Retrieval augmented generation is a good approach. A lot of people, when I have conversations, seem to think that, oh, we need to fine tune a model so that it can like answer questions about my company or my use case or my business or this particular thing that I have data on, and incorporate this knowledge. Actually, what's been shown is a recent paper showing that fine tuning in order to incorporate domain knowledge is possible, but it also that causes hallucination on other knowledge that the model was originally trained on, so can cause issues. Fine tuning, this was also OpenAI's recommendation, which I go along with, is that it's actually more appropriate for defining how the model needs to act. So if you have a specific structure of output, a particular format, you might want to output a JSON type string, which is a data format, or a CSV, or you may want a particular markdown structure or HTML, or just a particular set of paragraphs and formatting of the text. Fine tuning is very good in that respect, and I think that is where it really shines. I think it shines less in terms of including relevant knowledge. So you may want to use each of these approaches in turn to get your desired output, testing and iterating each time, making sure you've evaluated on lots of data, you've ironed out the edge cases. It can be really difficult to make sure that that the model doesn't hallucinate the wrong output, and really doing lots of evaluation to get that right helps. one other thing that isn't mentioned on this slide as well is optimizing the parameters. So the hyperparameters within large language models. So when you're using ChatGPT, on the web application or on your phone, you won't see these parameters, but hidden behind them. And if anyone who's used the APIs or open source models available, or they may have used the GPT Playground in the OpenAI's platform website or Claude's platform, you're able to control different parameters. So I won't go into them in too much detail, but one is temperature. So having a lower temperature essentially is a concept that comes from statistical mechanics, statistical physics, and the temperature essentially controls the degree of like randomness in the output. So a temperature of 0 means that the model will just select at each stage the most probable next token. But if you increase the temperature, that basically increases the probability that it may select one of the less probable tokens. If you've got like 10 candidate tokens, which is the next most probable word, increasing the temperature basically means it might select one outside of the top one, and it may be less consistent, but also maybe a bit more creative. So if you're doing like writing an essay, or you want some creative output, you might want a higher temperature. If you want something that's like going into another system or calling another API, you may have like a multi-agent system or something like that. You want a lot more control over the output. So having a lower temperature is ideal, maybe even 0 is common. There are other things you can control in terms of the frequency penalty, which penalizes the same token appearing many times if you don't want a lot of like potential repetition. The max token length, you may want to control the max tokens of the output. There are many different parameters that you can tune. There's the top P, the number of outputs, even the random seed, the random number that OpenAI uses behind the hood. You can control that if you want very deterministic output. And often that's one of the challenges with machine learning or deep learning based applications is software engineering is traditionally a lot more deterministic, and people expect things to be deterministic. If you're going to a website and you enter something and you press enter one day, you don't expect it to be different the next day in many cases. So that is one challenge, is making that the output of large language models as deterministic as it needs to be. And I think that is where some of these techniques can be used to get that kind of deterministic, consistent output. So I'll touch upon this very quickly because I think this is quite maybe an overly complex slide, but just to show you, like, this isn't necessary for every application, but this may be like a very advanced production large language model that uses all of these different techniques. So you may have an end user going to some user interface. It might be a web application or an app or a desktop application. They would enter their query into that. So this is basically the input. And let's give an example of a user going to like an education website and they want to learn about a new language, let's say. So they've entered, I'm learning about Spanish. This is what I know so far. Can you generate me some exercises based on my knowledge and my learning goals? So then the UI would then take that query. It would go to the embedding model and then find in the database where you've stored relevant data, maybe particular language exercises within a vector database. So it might say, okay, here are some grammatical exercises, fill in the gaps that we have in our database. Some, maybe have the solutions as well. And then there may be like a filter. So there may be like, okay, there's private data in there. You want to filter that out and make sure that doesn't get sent to the user. And then that may go as well as the initial prompt into your final prompt. So you've got your context and the user's prompt, the query and the context together. You may have even like a prompt optimization tool. So this is like an extra step. Obviously, there's cost associated with doing this, and it's not always necessary. But you may have another like large language model call that says, take this prompt and optimize it. If the user's just put in something very sloppy, can you actually make it better so the large language model gives a better output? Then with that optimized prompt, that would send to either an open source LLM or a proprietary API. And then before it gets sent to the user, you may have a content classifier or filter. So, for example, the Azure GPT-4 API, which gives a bit more professional control over the outputs. It comes with a content classifier and a filter, so that might make sure that the large language model doesn't put out anything, harmful or offensive. You may want different guardrails either with the user's input or the output at each stage, because people will try and jailbreak things. I saw one example of a company had that was like a car dealership had created a GPT-4 type chatbot on their website, and immediately people started trying to jailbreak it with different prompts to get them to say that we're going to give you a free car, or give them a full refund when it hadn't been approved by someone. So these are things that you can control with by having guardrails at the beginning and end, in either place where it's most appropriate, where the large language model might reject certain answers and it might say, sorry, I can't answer this. In many cases, if you have a very specific niche use case, let's say you're building a large language model for a bank, right? You don't want people trying to use it to, ask about where they should go on holiday or something like that. So like having those guardrails in place is really important. One other thing to mention as well is there is this idea of like caching large language model outputs. So if the costs are getting quite high, you may want to have certain common queries and outputs stored in a cache. So that just means that if a new user or the same user comes and asks the same question, rather than doing all of this and all of these costs associated with calling an API or running it locally on a GPU, you may just match the cached output and say, okay, here's the input. We've already got the output from a previous query. Use that. That is one cost optimization tool that's being suggested. So you can see you can go really far. I don't think in the first instance many solutions need all of these different steps, but there's lots of building blocks beyond just calling an API and being a GPT wrapper. And to be honest, many of those types of applications will probably get replaced by new functionality that ChatGPT or others have. Okay, so just quickly, some of the challenges of deploying large language models. Again, if you're running it locally, high memory requirements, long inference times, is it coming back quickly enough? You might want to use streaming, so you can stream the output token by token rather than waiting for the full response. And many of the providers like OpenAI and Azure have the ability, and things like Together AI, other open source providers have the ability to stream the output. Obviously, the cost at scale, having controls on you may want to have internal limits. If you're using a platform, just make sure that you have monitoring and warnings and limits set up so it doesn't go outside your budget. Then different deployment architectures. This is more gets onto the software engineering and DevOps side, but if you may want to deploy a solution with something like Docker or Kubernetes. You may be using a serverless deployment using something like Google Cloud Functions. Also, the big cloud providers like AWS, Google, and Azure have AI services. AWS has SageMaker, Google has Vertex AI, and Azure has Azure ML Studio and AI Studio. Oh, and AWS has Bedrock as well, which contains a lot of language models like Llama and Anthropic's Claude, or using APIs directly from providers like OpenAI and others. And then doing a lot of the things that are common not just for large language model applications, but generally, making sure you're having monitoring and logging of the outputs and inputs, tracking errors, catching and handling errors, using continuous integration best practices. There's the sort of DevOps skills, things that we mentioned around caching, ways of scaling to handle traffic spikes, and then different security measures. You may want to have, obviously this is more on the software side, but having authentication, rate limits so users aren't like hammering your API and racking up cost that you're going to have to pay for. But also like some of those content controls and guardrails that we mentioned to make sure that in this case, with large language models, people may try and get outputs that you don't want. So ways of having content controls and data privacy controls around that is important. Okay, so great. So I'll just cover some real world use cases, and I just encourage you to think of some real world use cases, and maybe if you can think of them, just drop them in the chat, so we can have a bit of a discussion and any questions you may have. So here are just some examples. So from across a range of industries, in consumer goods and retail, and for many brands, they monitor their public relations, what people are saying about their brands, are people complaining about certain product issues online, and large language models and NLP in general can look at consumer conversation either on social media or in their call centers and complaint centers to see if there are any issues that may be arising, common issues, and they can respond to those quicker. Call center automation. There's a huge industry around call centers within any industry, within banking and telecoms, within utilities. I'm sure we've all spent hours on call centers on holding music, waiting to speak to a real person, or maybe speaking to a chatbot and having a terrible experience because they're not very, very good often, and wanting to get to a real person. I really hope that this is something that large language models makes a headway in to improve that customer experience. Within e-commerce, using chatbots to answer questions about the retailer, certain products, maybe even helping the person shop and fill their basket with goods based on what they're looking for. Within media, a lot of marketing content, whether that's a social media post or a blog or a TV ad, we're going to see large language models used, and they probably already are a lot more there. So good and bad with that, maybe a lot more spam, but hopefully a lot better content as well. Within the public sector, so this could be, for example, within immigration or tax, policing. There's often very document heavy industries, and caseworkers are overloaded with documents they have to read and understand, and finding tax issues, finding understanding different cases, police looking through case files to find patterns within it. I think this is something that the public sector can really benefit from, and so using large language models there. Obviously in this, there's ethical considerations and privacy, security considerations. So if you're working in that space, I think really understanding the security best practices and data controls is important. Same with healthcare, again, a sensitive area, but large language models. There's a company called Hippocratic AI that are using generative AI to answer questions about from patients and give them like a summary of their test results, etc. So using large language, I don't like the term generative AI actually, so just sticking with large language models is useful there. Also electronic health records to help doctors. They spend a lot of time writing up case notes, so automatically capturing that could save a lot of time. We have a stretched healthcare system and an aging population, so anything that helps there is of great benefit. Within financial services, many financial analysts will sit on earnings calls and review financial documents. They might review quarterly earnings reports and try and give projections. There was a paper that came out. I always take these with a pinch of salt, but it was suggesting that the best large language models can actually outperform your average financial analyst on projecting the next quarter's quarterly earnings and profit, revenue, loss, etc. So yeah, hopefully maybe people working in hedge funds are going to have some tools to work with, or competition from more automated systems. And then within law, we spoke about law quite a bit. I think law is a very document heavy industry. and paralegals spend hours poring over documents to find relevant clauses, to update and rewrite legal documents in what's quite complex, like legalese, legal type language. I found large language models, very useful for not having to pay a lawyer to do something, or to analyze, if you're asked to sign a contract, just asking, can you summarize, find any key clauses that I need to be aware of, rather than reading everything. I don't think anyone nowadays reads all the terms and conditions when they sign up to many things online, and maybe large language models can help us out there. So these are just some ideas of use cases. I mean, there are potentially tens of thousands more, and I think that's kind of where it's exciting place to be in, is thinking about what the right use cases are, what the wrong use cases are. There's going to be a lot of challenges, I think, in building applications, and I'm actually surprised at how few, outside of using ChatGPT, how few applications you see that use large language models in the real world. Uh, in the tools that we use day to day. So if anyone has examples that they can point to where they've seen it, or maybe that they've worked on, that would also be fantastic to talk about. So with that, we'll go to the Q&A. Thank you all for listening to me speak for this long. I've gone slightly over actually, but if you're willing to stay on a couple of minutes, that's great. I'll be quick to go through the questions and answers. Okay, great. I'll just go to the top. Da, 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 da. Okay, here we go. Let me got this one. Q&A. Okay. Will we get recording? I believe this has been recorded, so yes. Oh, we've got the question answers here as well. Yes, Sam will be able to share the recording, I believe. Let me know if that's not true, Sam, but please do share the recording and the slides. Slides will be shared as well. It was until one is slightly over, so apologies for that. Okay.
I'm so sorry, Jon. Can you see the questions in the Q&A at the bottom of the screen?
Yes, yeah. I'll just scroll just to see how. Let's see. How can we apply? Okay. No, this is just some spam. Supply chain distribution use case. Yeah. Okay, that's interesting. Yeah, I can imagine supply chain has to deal with a lot of documents and tariffs. So that's a good example. Okay, so how does a token give or no assume the meaning of a context to a vector? How do you define the token? That's a good question. So the way embedding models are trained they will be trained on text. Well, an early version was called like skipgram. There are newer, more modern approaches. But basically, the way embedding models will often work is they will mask certain tokens in a text that it's trained on. So let's say you have like loads of text about like news based, like BBC News, right? And you're training an embeddings model to understand BBC News text, or just news text in general. And let's be more specific. Let's say you're looking at news text in the 19th century, so like quite old-fashioned text. And the language there and how the language interrelates. What you might do is you might take all these historical news articles from archives, and then the embedding model will mask certain tokens, and then you'll train a model that can try and predict what the token is and minimize the loss by the model learning how to predict the masked token. So you're basically creating like a training set without labeled data, just by masking tokens, and then the label is the masked token. And through doing that, the model can learn like what tokens might easily be replaced for another. So for example, if in that 19th century text, it might say a word like intelligent, right? Or idiots, right? It might say another word. It might be like this person was a no, maybe trying to think of a good old fashioned term. Yeah, maybe this person was a bit of a sleazy person. So they may say, oh, another word for like sleaze is like a CAD or a bounder or these kind of like old English, bridge, some of these 19th century terms, a rogue or something like that, right? And so it'll understand the relationship between those by through this process of masking tokens and predict, and then the model learning the weights to best predict those mass tokens, and that's how embeddings are learned. And then from that, you'll have a model which can understand that, dog is to puppy as cat is to kitten, and understand those relationships that we have in language and get like a deeper understanding of what words mean. Because we understand words, it's not just like an individual token with frequencies it may appear. It's they have some relationship between one another, and that's what embeddings help understand. Okay, the next question: when answers are available for a specific user question, how does the model choose what to pass to the user? Oh, okay. Well, as I mentioned before, it will predict token by token. You can also have the large language model output like different candidates, like 3 different outputs, and select the best one. But it really depends on the use case. Like I think let's say you're using the RAG approach and you have different answers. You may want to just choose the most probable one, or you may want the model to output like all different answers. Just try and be safe and try and, make sure you give the best probability of getting the right output. Whether that means, showing multiple outputs and references is often helpful, saying, okay, here's the output, but here's a reference you can click on and see where it came from. So you're absolutely sure you can check yourself that the model hasn't hallucinated. Here's where it is in a document. That's also helpful. How does it recognize the probability? So the way a neural network will work is you have input tokens, and it will then with a forward, once it's been trained with a forward pass inference time, so that's a prediction time, it will pass through all the different weights of the neural network, and then at the end you'll generally have what's called like a softmax layer, and that softmax converts the different weights in the final layer into a probability per token. So it'll basically convert per token a probability, and then you just select the one that has the highest probability. I think if you want to understand that, there's probably some good online resources I can share around how that process works. Do you have an example of an LLM roadmap for program or project level? Okay, that's a good question. Yeah, so if I'm guessing you're coming from more like a direct level, more senior, and you're understanding like how to lead a program. I'm going to do a little bit of a plug here. I'm writing a book called Data Science for Decision Makers. So that may be a good way of understanding. That's more for people on the business side, to understand like how to set up a team or a program. I think the key thing is it'll be on Amazon. Hopefully I can share the link. But yeah, this is more for like business people, decision makers, executives, or maybe someone stepping up from a data scientist to lead data scientist. But I think the starting point when looking at a program is understanding the business value and use cases. Having enough knowledge, you don't have to be an expert in the mathematics behind large language models, but having enough knowledge to know like what works well, looking at other industries and where they've had success, or other companies within your industry, and then looking at the use cases and saying, okay, these are the top use cases. What do we need to achieve these? What data do we need? What systems do we need to connect to? What skills do we need? Is it going to actually make a tangible difference? Because you can spend loads on a program and bring in hire loads of data scientists, which, by the way, generally isn't the best idea. You want like a range of skills, data engineers, software engineers. You might want other sorts of skills to complement ML engineers, people who've done this before, right? And then make sure you've selected the use case that's going to actually change, affect the bottom line, affect the profitability of your company. That's always the starting point with any program, I think, is like, okay, here's our roadmap based on these use cases. Some we can't do right now. And also you can think like, okay, LLMs and multimodal models, maybe they can't do things now, but you can bet with some degree of confidence that they might be able to do them in the future. So looking at that roadmap in terms of what sort of data do we need, what infrastructure do we need, what skills do we need, and then like work through smaller use cases. Don't just like hire people and like expect a data scientist to have magic. It's like, okay, start with a specific use case. Maybe the first one might not work as well, but like get some success and show one example working, and then you can look at other use cases and build upon that foundation. So that's how I would think about any roadmap, is like start small and fast and iterate quickly, and don't like hire loads of people that you don't know how they're going to fit. Maybe hire a strong technical lead, I think always helps to guide that process. There's many different things, but look at what companies have done well here, because many companies and many ML projects unfortunately never make it to production or fail. And I think you can learn a lot from other people's experience and working with people with like strong technical skills who've proven to have delivered this successfully in the past. Can it process volumetric or density calculations that are 4D? I'm not, or geographic data. So my understanding is, well, with these multimodal models, they can analyze images, right? 3D and 4D, not that I know of, there aren't many multimodal models that like, for example, GPT now 4.0 can take images and output images, etc. But they're not handling like native 3D. I have seen some like text to 3D models, but as far as I know, there's not any like state of the art model to understand geographic data. I think if you're looking at geospatial analysis, there's a whole area of geospatial analytics and geospatial machine learning, and there are experts in there. There are tools. There's one called it doesn't come to my mind. There's some great, there's ArcGIS and others that are great for geospatial data. So I think at the moment, using large language models probably isn't best for geographic data, but working with geospatial experts, and there are loads out there, that's going to be your best bet. Or some of the geospatial tools like ArcGIS, etc. Okay, if we have an LLM today, why are they not common for debugging code and suggesting corrections? I think they are common for debugging code. Like I think even with like, if you're using GPT-4, they may not be perfect, but GitHub Copilot is also useful for programming, and there are specific code models. The French company I mentioned the other day, earlier, sorry, Mistral, they've released a code, I think Code Mistral it's called, like an open source model for code generation, and I think that's going to be an area that improves a lot, and it's going to save a lot of time for software development. But we'll see how that goes, and I think there's always going to be the need to have senior people review and understand that code, and I think there's also the chance that just using large language models to generate loads of code is going to cause a lot of bugs and issues as well. So be careful with how you use that. What are the LLM models mainly used for? I think right now, like basically answering questions, like the way you would use it as a user on ChatGPT. I would suggest that that's probably the vast majority of how people are using them, and companies are using them. Really, I don't think that there've been as many applications outside of that as you may expect. If it requires systematic training and conditioning to you agree it's essentially a vetting if function in computer science terminology that around for decades, the complexity being marketed essentially data science processing as the 90 reverse engineered algorithm management where software application is deconstructed and then repurposed as a funnel for language augmentation. Software programs that collect targeted data and then packages a solution are simply a less specific method of the same objective as well as outputs. It also relies on outcomes that are only as complex as the end user, so LLM can only maintain at the rate of education. I think there's a couple of things there. I think to say that it's just nested if statements is maybe oversimplifying it. But I think on the other hand, people are maybe overstating the capability. So it's somewhere in the middle, I would say. It's definitely not only if statements. I mean, if you look at the architecture of like a transformer-based model, it's not nested of if statements. Yeah, it's not, it's more than nested if statements. There's a lot of complex architecture within a neural network, and the training process involved with backpropagation, and reinforcement learning with human feedback is, yeah, it's a lot of mathematics that goes in there, and it's more linear algebra really, which has been around for century, over a century, than if statements. I would say the underpinning is more maths rather than computer science, but obviously, it's programmed with programming languages and frameworks like PyTorch. But having said that, I think the other extreme is to say we nearly have AGI. Uh, Large language models, they're not able to come up with new physics, new science, even new information really. So it is, you're right in saying that it's as complex as human knowledge has, right? So it's basically like the sum total of everything that we've learned, and it's showing us back that way, and it has much better than a human at memorizing things, right? If I asked people, what's the state capital of Kentucky, right? A large language model is obviously going to know that, but like most people can't retain all that information. But more deep thinking, reasoning that isn't required for, I can't do this sort of thing even, but like or, uh, nowhere near, but like the reasoning that's required for pure mathematics research or biological research or new physics, we don't have that. And I don't think even just scaling up large language models as they currently are, I don't think it's going to get us to that stage, to get us to AGI. And I would say that if large language models can't do new physics, it's not really AGI. And I do think we might be hitting some asymptote, some local flat point, because we're on an exponential, but an exponential more like step function going up like this. My guess, I'm not an expert in this, but reading people like Jan LeCun and others, it seems that large language models may peak a little bit until we have a better architecture to do more of that complex reasoning. So yeah, I don't think just like scaling up the current architecture is going to work, but I wouldn't say it's just if statements. There's a lot more going on there. Can't be used for genetics, cancer. No, not directly. I mean, transformer-based models are being used for genetics, like protein folding. AlphaFold from Google DeepMind is coming up with new a drug discovery. It's being used for that. So they are being used for medical drug discovery. But it's often part of a bigger system. It's not, you're not just going to ask like ChatGPT cure cancer. So there's a lot of work that's going into using large language models and transformer-based models. And what's amazing is that it actually works, like how the transformers architecture has so many applications outside of large language models, and it's being used for drug discovery, for new mathematics. Even there was I mean, not directly, but there was a DeepMind have used large language models to produce candidates. Not so it's not at the scale where it can produce new mathematics, but it was being used as an assistant to come up with new mathematical proofs, I believe. Okay, sorry, I rambled on there. Is there an LLM architecture role or concept? I haven't heard of it that often. There's going to be like LLM engineer, and software architects, AI architects. I don't really think that having separate architect roles is always the best approach. I think that having architecture skills is useful, but I worked in a company where there was an architecture team, and they do all the upfront architecture and they hand it over and say to a software company, a team, or an ML team, build this thing, and it never matches up with what software's not like building houses. That there's chance to iterate, right? So it's like an ongoing process. So yeah, I think people think they're like, you have the architecture stage and then the development stages. No, you have some upfront design, but there's continuous process of designing as you're developing, right? So I don't think that like having architect and having architecture skills and engineering skills is important, and doing solution architecture is important, but saying, oh, I'm just going to be an architect and do UML diagrams and someone else is going to build it, I don't think that's gonna. I don't think that works very well in practice. Uh, yeah, I've got some agreement there. I'm glad to hear. What's the difference between embedding and encoding? Embedding. Oh, okay. The embedding definition I gave earlier, encoding. I think maybe that's to do with like voice encoding. I need to understand the exactly because encoding is used in a different way. Like it could be text encoding, like for example UTF-8 and stuff. That's a whole different thing. That's just different. That yeah, that's more about how you're storing text. If that's what you're referring to. What hardware is used in the production logistics scenario to minimize latency? Oh, so well, if you're self-hosting, you might use different GPUs or parallelizing outputs. So to minimize latency, you know, there's different techniques to do that using better GPUs as they become cheaper. That could be one. Or by streaming output. How can we ensure the foundational models we use do not contain implicit bias in how they are processed? Good question. I think bias is like a broad topic. I think that all models will have bias because of this reinforcement learning from human feedback technique and the decks they're trained on. They may, you know, if you train on Twitter data, you're going to have a very probably offensive, biased model. But then it also, you know, everyone has their own biases, and I don't think necessarily the biases of the people working in Silicon Valley reflects, you know, what the broader population believe is true. So it's a good one. I think that I don't have time to get into the ethics. I think it's a whole minefield. But I think in my opinion, the best thing these companies can do is be more transparent. And open source is the most transparent. So I hope to see more transparency. Okay, how easy is it to test use cases with MVP or POC concepts, blah, 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 etc., etc. What could be a good starting point? Yeah, I think it's more like a project management approach. I think, you know, I think the agile it works to an extent, like as an approach. Building sort of like a working version of something if it's not perfect first, and then testing it, evaluating it, seeing if it's going to be valuable. Getting to that stage quickly is always a good. And also failing fast and throwing out bad ideas. Like if you do a POC and it's not doing what you wanted it to, or it's not going to deliver value for a business, or it's hallucinating too much to be useful or safe, then throw it out. Like I think that's also something that is often overlooked is failing fast. Do you want if I want to deploy an LLM based app for portables Android, how can you deal with the lack of signal connection? Could you host locally an LLM? There are models like Phi 3 that are coming out, which are smaller models, which may be able to, you know, in the future you can have locally on an iPhone or an Android. And that, I think also the chips to run that on phones, you're going to have like AI phones, and Samsung are talking about AI features, and Apple are going to do the same. And I'm guessing you will have local, but from what I understand, you can't like use an Android and to run in any useful way LLMs locally within an app. The signal thing, I think that's just the same as with any app. Like most apps require, no, not most apps, many apps require internet connection. And I think with the availability of like 4G, 5G, or, you know, Wi-Fi everywhere, I don't know if that's always a big problem. Maybe there are certain situations like remote situations where that's necessary, but I would just treat it the same as like if you had to call a remote server. You know, if you're using Uber, you know, you're calling their server, you need to be connected to the internet so you know where the car is, right? So I think it's the same thing. Like we don't local's nice, but I don't think it's always necessary. Can LLM couple with geospatial tools as the input method? Yeah, for sure, potentially. I mean, I'm not an expert on geospatial data, but I can imagine, for example, Google Maps in the future, you know, you type into Google Maps like find me a restaurant that serves, you know, pepperoni pizza or whatever, and the large language model looks with the best reviews. It reads the reviews, it reads the menu, it says, okay, here's this restaurant that has people really like the pepperoni pizza at this place. or where's the best coffee, or I'm looking for like gelato or whatever, uh, and that's kind of geospatial data from um, and reviews data, text data from something like Google Maps. I'm sure that will integrate in some way. So I'm sure like when you're asking questions about um, geospatial information, that's going to be all integrated. Can LLM couple up with geospatial tools as the input method? Oh yeah, sorry, I answered that one. That's yeah. So I think that they're bound to be. I don't know how seamless that will be, and there'll be definitely points where geospatial tools are more appropriate. But I'm sure that there's going to be many map sort of tools which have LLM inputs. What expansion models do you believe will be most effective to make LLMs part of culture? Oh, I think by part of culture, maybe that means like how is it going to be more common part of culture, like commonly used? Is that what you mean? Or I don't know if you mean like more in terms of like culture, in terms of like music and art and things. I think just more people are using them. I think like with um these models being provided for free and also being more common in other tools like Google Search or Microsoft Office, then it's going to become just part of our culture and as common as Google. I don't think there's yeah. So uh, I think it's already become very common, and many people have used ChatGPT who aren't technical. So I'm sure that's gonna expand, and I think it's great because it's democratizing things. You could be living in Madagascar, and you're able to have all this information at your fingertips and have like a personalized tutor to learn about machine learning or whatever. So I think that's only a good thing. Okay.